Regarding myself, my name is Alok Kumar. Currently, I am working in FCC block of Vizag Refinery. Uh, I have been coordinated for you people to give introduction part regarding virtual internship program for the FCC block. So mostly I'll focus on covering the FCC part, but I'll touch the refinery background also. So let everyone come. After that, we'll proceed. Okay, we'll start the session because time will not be there. It's a one hour session only. So we'll try to have a intro like interactive session. So as I told myself, Alok Kumar, uh, I have a working experience of 8 years. I have worked 3 years in Reliance uh, Jamnagar complex in the gasification complex. That is to 3 years of commissioning. So 3 years of commissioning I have. Then I have worked Veena refinery also 2 years. Then 3.5 years back I have joined HPCL VR refinery, and here I have been working into the FCC block. So I'll try to give whatever the knowledge, industrial knowledge I have gained throughout the industry. I'll try to give uh, maximum extent possible. So is the screen visible to you guys? Okay, so basically FCC virtual internship training is there. So it is very difficult, that giving regarding the refinery, give a touch by just the presentation or session is like a college session only. But based on our experience, we'll try to give you a feel of the industry. Okay, so in VR refinery, we are having two FCCs. One is we call as a FCC2, Fluidized cracking unit, and one other is FCC1. So basically, these two units are basically have a different licensor. Ours is I'm working in FCC2 block. Its licensor is EOP, and the FCC1 is basically ExxonMobil. Ours basically FCC. The difference between these two FCC, we have a catalytic circulation. What we establish, it is basically slide valve controlled. And here in the FCC1 we have a pressure balance control unit, right? Now just you see it here, how is this FCC block evolution have happened over the time. So it's not a within 5-10 years this technology is evolving. It has been evolving since 60-70 years. See, 1942. Since after that it is, see, over the time it is upgraded into the different technologies, and upgradation of equipment had happened. See, 1947 to 1948 first EOP stacked FCC unit was built. Then 1955 EOP introduced side by side design. Then 1956 Cell invented riser cracking. You may not be able to relate because once I'll give the process flow diagram regarding equipment, you'll get to know. Just I'm telling regarding the evolution of FCC. Then over the time 1974, Mobile Oil introduced CO promoter. Then 1983, Mobile reported first commercial use of ZSM 5 octane olefins additives in FCC. So different technology, catalyst upgradation, all those things had happened over the time. So you see total all over the world around more than 350 FCCs are there. In the VR refinery, if you see, I'll tell we have a 2 FCC, 2 FCC. Exxon model we have a 1.22 mm TPA. Then EOP model we have a 0.97 mmTA capacity. These are the major 6 licensors of FCC. ABB Lamas Global, ExxonMobil, Exxon Research and Engineering, then Kellogg Brown and Root, KBR. We normally it is famous as a KBR. Then it comes to Shell Oil Company, then Stone Investor Engineering Corporation, then EOP. EOP is the licensor or the technology giving to FCC2 unit in which I am working. So these are a slight difference between these two models. I'll not take much time for this presentation. So ours FCC2 is basically OP model. I told this is the capacity. Here FCC1 is Exxon model, 1.22 mmTP of capacity. In FCC2 model, we have a reason pressure higher than the reactor pressure. In the FCC1, they will have a reactor pressure higher than the reason pressure. Okay, these are the some differences that after explaining the total projection, you'll be able to understand these differences. Meantime, I'll go for the content, major content, what I'm going to deliver to you guys. So FCC, basically, what do we do here? So the content that we are going to discuss here, wait, what is FCC process, then FCC configuration in refinery, then FCC process description, FCC catalyst, FCC additive, different types of crude and its effect on FCC. I'll be telling. So is this diagram visible to you guys? So basically, this is the process flow diagram of FCC block, typical process. So what happens? I'll explain. We get a feed, correct? We get a feed. From feed, it is goes to FCC unit, FCC block. We'll be getting the different products. ATG. So acidic tail gas basically is a fuel gas, untreated fuel gas. Then we'll get from is LPG. You guys know about LPG? Then we'll get CRN product, cracked run naphtha. Then we'll get LCO. Then diesel HCO we get. These two are diesel compositions. What we are getting, these all are untreated. We have sent it to the other units for the refining purpose. Then after HCO, we'll get CLO. This is the products we are getting from the main fractionator column and the GCU section. Then after that, from region side, we'll get a flue gas. Flue gas, it will go for the further processing in power plant for waste heat recovery purpose. After that, it will be treated in FGDU for desulfurization unit so that it should not pollute the environment. After treating, it will be released to the atmosphere. So these are the products what we get it here, correct? That basically are in the untreated condition. So ATG will be sent into the SRE unit for the treatment, sulfur recovery. After that, that fuel gas we are getting, we will be using into the we'll be using it into the refinery for the fuel consumption purpose. Then LPG that we basically use into the household purpose, correct? Household basically for burning, cooking purpose and all. So this is untreated. Again, it will send to the Merox unit for the further treatment and all. After treatment, it will send to the bullets. From that, it will be transported to the respective location for selling purpose. Then CRN, cracked run naphtha, basically is a petrol. If I'll talk about the petrol, can anyone know what we are getting the petrol in your vehicle, bike or car you are filling? What is the composition? Composition in the sense, RON, how much is there? Anyone know about octane number or research octane number? Actually, the product we are selling to the market is not like that. Just like we are producing cell, we have to maintain a particular specs for that. If specs fail, we cannot sell into the market. So we need to 100% pass that test. Lab test will be there. So for that purpose, RON will be there. RON we have to maintain minimum 91.5 research octane number. Then yeah, octane number you can say. Then after that, we have a H2S content will be there, benzene content will be there, carcinogenic. So what are the minimum composition? These are impurities. We have to keep it minimum. So our whatever the CRN we are getting in FCC block, cracked and naphtha, is RON is already around 93. Because if it has a more double saturated compound or cyclic compound, because of that it has a more RON. So it is the product CRN we are getting, it is directly we can send it to the blend. Like we are getting naphtha, straight run naphtha, heavy naphtha we are getting from CDUs. We cannot sell it directly because it does not meet the spec. Spec in the sense specifications. Suppose SRN is there. Its RON will be lesser only, straight run naphtha around 73, 74. Heavy naphtha will be slightly higher. But after processing it into the isomerization unit and the CCR unit, its RON upgradation will be happen. So overall, they'll go for the blending, and objective is to maintain the RON more than 91.5. But here in our FCC block, we don't need that upgradation. Already the RON we are getting, it is of spec, only treating required. So it will go to the CRN, will go to the FCC NST, naphtha hydrotreating. There will remove the H2S and all. After removal, directly it will go to the blending purpose. Then after come LCO-HCO is the diesel. We'll be sending it to the DHTS or diesel hydrodesulfurization or diesel hydrotreating DHT unit for further treating. So after treating, we'll get a diesel that we can sell, send to the tanks. From tanks, it will be transported for selling purpose, or by either by pipeline mode or by uh, tankers. Then CLO is basically low value product that we get. So CLO basically we use internally also for selling purpose. Normally the ships we see in the seas and all, they mostly consume, or we will burn the CLO into fuel oil grade, will make it into the fuel oil grade, and that we use into the our heaters only for burning purpose. Flue gas already I have told you. So you see it here, feed, this is, and what are the products getting? This is the, these are the products we are getting. Feed is basically low valuable product. What? Low valuable product. So FCC feed is basically LVGO, light vacuum gas oil, HVGO, heavy vacuum gas oil. Other units may heaviest whatever the bottles will be there, that we can process into the FCCs. So basically LVGO is very low value, and here we are upgrading this much value. So that's why FCC plays a very important role into the refinery, and it is the one of the most profitable unit in the refinery. That's why its value is huge into the refinery. If FCC goes faster down, there is a huge loss for the refinery. So we make sure that FCC unit should run continuously without any problem. Is it clear? Till this part? Any doubt? Okay, that's what I told you. FCC means you can see it here. Fluidized cracking unit, secondary processing unit, profit margin of a refinery, high value product from a low value product, we get it. So basically, what we do, why residue upgradation is important? To upgrade heavier distillation cuts into lighter products. That's what I told you there. Then this is the products already, I have already told you regarding this products. You can see this is the feed. Once you process to the refinery, you'll get ATG, gasoline, light cycle oil, heavy cycle oil, CLO. Then coke. Coke basically it is getting burned into the regenerator. From there we are maintaining the heat. So now come here. This is a existing refinery block flow diagram. You know about the VR refinery. Earlier we had an expansion, now VR refinery. Any of you heard regarding Visakhapatnam refinery BRMP project? No, okay, I'll give a touch. See here, you can see we had a earlier CD1, CD2, CD3, three units. We have a crude distillation units. From that, you can see we get a VGO. VGO is basically LVGO as VGO that we goes to the FCC. From FCC, we'll get a major product naphtha. Will go that cracked naphtha will go to MS block. MS block basically it will go to the FCC NST. From there, after treating, we'll get gasoline. So this is the gasoline pool blending. Similarly, the diesel we get is basically goes to DST or DSDS unit. From there, we'll be treating, we'll be getting the diesel. CLO basically it go to the fuel oil. You can see it here. That will be using that we will be using into the burning purpose. So this was the existing refinery. Now current refinery of FCC, we further got one more CDU4 is there. I'll not go into the details of this because this is not much related to you. So we have a further one unit we got 9 mmTPA capacity CD4. We got new isomerization we have got in BR refinery. Then after that BR one HGO hydrogen generation unit we have get it. Then BRMP SRU is there. HU hydrocracker one FCHU is there. Full conversion hydrocracker unit. This hydrocracker unit objective is kind of similar to FCC. In FCC basically the fluidized cracking is there, but in hydrocracker it is fit. Moreover, HU objective is also to give a upgrade the residue bottoms. Then one rough unit is there. Whatever the bottom's yellow one is all coming, it is going to process into the rough. From rough, uh, diesel useful content will get, and the further the bottom will get the pitch. So I just told about regarding the FCC overview. So something here you can see FCC overview or process description. I'll go into the details of this. So you see, this is the feedstock I was telling. These are types of feedstocks we are using. We process into the FCC, and these are the typical products we get it. Okay. Now, if you see it process description, basically FCC we have divided into the 4 parts. Now I told you regarding feed, then we process into the refine FCC, then what are the products we get. Now I'll tell in between the feed and product how our unit operates. So basically FCC fluidized cracking unit have mainly 4 sections we have segregated. One we call it a feed preheat section. Other is RR section, then fractionator section, then gas concentration unit. So first of all, that feed we get is basically comes to the. Am I going fast or is it okay? Okay, so basically one by one these 4 sections will uh, try to complete, and basically after completion of these 4 sections you will be able to understand how FCC plant works, what are the feed, what are the products we get, and internally what we do actually. Okay, so one by one 4 sections will discuss feed preheat section, RR section, fractionator section, and gas concentration section. Now I'll tell about the feed preheat section. Okay. So see, you try to see it here. This is the feed system. Basically, feed we get right. This is the cold feed. What happens? And one will get a hot feed. So what is the difference between these two? Basically, cold feed we get it from the tanks. And suppose this CDUs are there. They are generating LVGO and HVGO, right? LVGO and HVGO. So LVGO and HVGO basically are the feed for our unit. If this LVGO and HVGO after coolers, it is going to tank. It can route to the directly our unit at a hot feed, or it will go to the tanks through the cooler. It will go to the tank. From tank, if we are getting, then it is called as a cold feed. So both the feed we get into the feed system. For feed system, feed pump is there. So this is the vessel where we maintain a minimum level so that pump will not cavitate, because for pump run minimum level always we need to ensure, right? So basically from feed pump, pump will take a section from the feed pump get a discharge. It will go to preheat exchanges. This is the preheat exchanger. Set of 3 exchanges are there. Through that is there. And basically FCC fluidized cracking unit. We have to crack the feed. At what temperature this cracking will require? Because the reaction, right? Anyone can guess what temperature this is? How much? Okay. Moreover, 500 to 530 range will be there, right? 500 degrees Celsius to 530 degrees Celsius range would be there. As of now in FCC, we are operating this range. Currently, our ROT, reactor outlet temperature at which endothermic reaction will happen is 520 degrees Celsius. Around we are maintaining 520 to 525 degrees Celsius we are maintaining. So see, here the feed we are getting hot feed around 200 degrees Celsius. Here cold feed get around 70 degrees Celsius. Both combined together here will get around, based on the how much hot feed we are taking, around uh, 130. Matlab, if total cold feed is there, then 70 to 130 or 150 will be maintaining. Now, at what temperature this reaction will happen? 520, right? So how we are going to achieve this temperature? Objective. First objective, how we are going to achieve the ROT. If you understood how ROT we are getting able to achieve, you will understand the total RR catalytic circulation, FCC catalyst circulation. Okay, so first up, suppose this temperature 130 degrees Celsius, it will go to the feed preheat exchanger. The you are seeing the tube side will be there slurry. Whatever the bottom we are getting the main fractionator column, from that bottom it is getting heated. So once after this 130 or 150 degrees Celsius feed, we are heating here. After it is getting heated, it becomes around temperature of 250 degrees Celsius. But further, this reaction will not happen to 50, right? We need how much? 520. So how we are going to achieve this? This is further going to heated here. So we have a charge heater here, direct firing heater. If you uh, have read during your college time, then you might be able to understand. Basically, here we'll give a direct firing. After that, it is getting heated into the uh, this all the this feed will be into the coils. Coils will be there in the form of coils. It will run through the heater sidewise. After getting heated, this temperature will be increased to around 280 degrees Celsius. Okay, 280 to 300 degrees Celsius. So after it is getting heated, then it will go to the through the feed filters. In feed filters, if any contaminants or anything is there, we'll try to it gets filtered. After that, it goes to the reactor. So this part, what I was going to look, what I am telling is this part is basically feed preheat section. I was telling, right? The four sections I'll be discussing. So this is the first section, feed section. So basically, from this temperature to making it 280 degrees Celsius, what is happening all over here is basically preheat section. Now we'll go to the RR section. See, in feed preheat section, you just remember how much temperature we have got? 280 degrees Celsius. Clear? Is it clear? Okay. So in feed preheat section, how can you tell how much temperature we need to achieve or we get from the feed? Can anyone tell? See, uh, correct. So in feed, very good. In feed preheat section, we are increasing the because the reaction will happen as 520 degrees Celsius, right? We have a 280 degrees Celsius as of now we are able to achieve. Now next objective we have to achieve 520 degrees Celsius. That we are going to achieve into the RR section. So I'll now next uh, session that I'll tell now is regarding reactor regenerator section. Okay, let's move further. So RR section basically consists of one reactor will be there and one regenerator will be there which together with the standpipe riser forms a catalytic circulation. So basically this is the reactor and this is the regenerator. This line you can they is basically standpipe of spent catalyst will flow through there and this is the regen catalyst will flow here. From here the feed will come. I am telling now how feed at what temperature feed we are getting 280 degrees Celsius. The 280 degrees Celsius feed will come here and basically from bottom this is the RCSB through RCSB regenerated catalyst slide wall through that regenerated catalyst will join here into the riser. Bottom lift steam will be given that will lift up the steam and total together it will club with the feed and feed will go through the optimix nozzle. Basically it will be immediately, it's not like that in liquid form, it will go through vapor kind of vapor form. It will vapor in the sense it will immediately through the nozzle it will vaporize and through this temperature the feed from the bottom the RCSB region catalyst we are getting now both together will go to the reactor riser. So most of the reaction will happen into the reactor riser. This is the reactor riser. So most of the reaction we get it 95 to 97% reaction will happen into the reactor riser. So this temperature, once this hot catalyst is combined with the feed, the temperature will immediately increase to 520 degrees Celsius. How the catalyst now, how we are getting 520? What is the heat source here? Can anyone tell? Exactly. The source is regenerated catalyst. What you can interpret it here? The regenerated catalyst temperature must be more than 520 degrees Celsius, right? Because it is combining here with 280 degrees Celsius and giving a temperature around 520 degrees Celsius, means this temperature should be more than 520, right? So in region catalyst, the temperature here we maintain around 700 to 720 degrees Celsius. Plus minus can happen based on the feed unit conditions and all our emergencies. But normally we try to maintain 700 degrees Celsius to 720 degrees Celsius. Also, if the feed varies, this temperature can vary based on the lighter feed we are processing or heavy feed we are processing into the CDUs. Accordingly, LVGO and VGO sulfur content will vary. Is it clear? Someone should respond, or else it is very difficult. It's like just I'm giving a presentation to laptop. At least 1 or 2% give a positive response. Okay, one video I'll play. Try to see animation video is there. Try to see this RR section videos. Okay, wait. Can you guys see it? Now you can see. So see if you see it here. This part I'm indicating here. Arrow mark. Can you see my cursor arrow mark? So this is the basically reactor part. This is the regenerator part. This is the slide valve, spent catalyst slide valve. This side is regenerated catalyst slide valve. Whatever the reaction will happen through the reactor vapor line, it will come to the main fractionator column. Then whatever the flue gas is there, that will go to the further orifice chamber. From there, it will go to the waste heat WHRS, waste heat recovery wallet. There it will get treated, and then it will go to the FGDU for treatment purpose after the heat recovery for further treatment. Then it will flue gas will be exposed to the atmosphere. So overall, how this reaction will happen into the RR 520 degrees Celsius we are maintaining. This how catalyst circulation is going to happen is happening in FCC. You will see it here. Okay, I'll play the video now. Is it visible? Okay, is it visible now? Cursor part, can you see this cursor part? Okay, so you see, I was telling right, if 520 degrees Celsius we have to maintain. So we are getting around 280 to 300 degrees Celsius feed. So what will happen? Feed we will be getting. This is the regenerate. This is the regenerator. This is the reactor. This is the, you can see. This is basically spent catalyst slide valve, and this is the regenerated catalyst slide valve. So you can see the smart particles coming here. So this is the regenerated catalyst will come, and this will be lifted out with the lift steam. Lift steam basically we give as a MP steam, which will lift the catalyst and it will combine with the feed. So most of the reaction, this is the long wait. What you are seeing here, this part you are seeing vertical part. This is called as a riser, correct? Now the 97% of the reaction will happen into the reactor riser. So basically hot catalyst we get, it will combine with the feed, the reaction will happen here, right? So this this temperature, region temperature around 730 degrees Celsius and 700 to 730 degrees Celsius, and the feed temperature would be around to 280 degrees Celsius. Both clubbed together will get a 530 degrees Celsius. 530 degrees Celsius or 525, whatever the ROT we are maintaining, that temperature will get. At that temperature, reaction will happen. So once reaction happens, now the composition, now after reaction mixture, it will have a catalyst, right? Catalyst it will have a, and it will have a reaction vapor mixture. Okay, in the reaction vapor mixture, in the LCO, HCO, diesel, everything will be there in the vapor form. So how catalyst is getting separated and how the reaction vapor is getting separated, in this animation video it is visible. You can see it here. See, this is the traveling. It is going right. It is traveling like that. So this is called BSS chamber. Vortex separation system will be there. In that 120 degrees Celsius vertically, that this reaction vapor mixture will get separated. It will hit on the walls of the BSS chamber. And what will happen? The catalyst, uh, what will happen after that? Catalyst will start falling, right? So this heavy product, the catalyst, will fall through like this. This is called reactor stripping. If you see it here, see. If you see it here, it is falling right here. So it will fall under this section is called a reactor stripper section, right? So catalyst is falling under reactor stripper section. The objective of reactor stripper section is to whatever the entrapped hydrocarbon is there, not coke. Hydrocarbon is there, will give the stripping steam to strip off whatever there. So the hydrocarbon should not come into the region or hydrogen, whatever the lighter products are there, it should not come to the region. If it comes into the region, it will burn air and further region temperature will going to increase. So we have to control the region temperature also and reactor temperature also, right? It's not like that total circulation will happen. Will control the circulation. How much catalyst need to come into the reactor will be decided based on the ROT. So suppose catalyst slide wall opening is 40% and ROT, my ROT is 525 degrees Celsius. ROT coming down to 520, then what will happen? Our slide wall will further open so that more catalyst should come, into the reactor so that temperature we can achieve, right? So this is how regenerator slide valve will operate. Now the reactor vapor mixture will go here through the BSS. It will fall on the reactor stripping section. Stripping system will give the steam. Now here will maintain the reactor label. Cursor you are able to see. The cursor, guys, you are able to see my cursor. So what happened here? Minimum label will maintain. Now label in the sense the catalyst level will maintain. So here one slide valve will be there. What we call it a spent catalyst slide valve. So we maintain the reactor level around 40 to 45% will maintain. If label catalyst taking more, so this spent catalyst valve opening will be more. Suppose 40% we want to maintain, the label increase to 45. Delta 5% delta created, right? So what will happen? The catalyst will open, the slide valve will open further so that the catalyst will go into the region. So this is how catalyst circulation will establish. So catalyst circulation establish basically two things are required. One, ROT, reactor temperature. How much reactor temperature we want to maintain. Second is basically the label, how much label we are maintaining. So based on the catalyst circulation will happen automatically. Continuously catalyst will come and it will float. So after spent catalyst, what will happen? On the carbon will be there. It will come to the regenerator here. Burning will be happen. And the burning will basically, it will burn how? We need to give air. So for that, main air blower will be there. And here complete combustion will happen. Okay, now you see it. This is the stripping happening. You see it here. After that, you just keep searching. This is the burning is happening over here. Now you can see after BSS chamber, it will go to the reactor cyclones. These two are the single stage cyclones. The objective of cyclone is to basically remove the catalyst particle based on the centrifugal force. So basically, it will enter both the cyclone. Two cyclones we have in our reactor through the catalyst. Here bottom it will not be totally open. It is a trickle valve will be there. Some hold up of catalyst will be there. Once suppose counterweight plate will be there. Suppose it is going to some weight will be there. If more than that weight catalyst hold up is there, then slide valve, this trickle valve will open. Counterweight valve will be there. It will fall here. Similarly here, and then the from the cyclones vapor will go from the cyclones. It will go to the through reactor vapor line to the main fractionator column. So this is how total reactions is happening. ROT we are maintaining 520 degrees Celsius, right? How we are getting region catalyst. Once catalyst we are getting, we are allowing the reaction to happen. Once reaction happen, our objective is to remove the catalyst, and so that reactor vapor mixture. So here separation part will do, and the reactor spent catalyst after the reaction, carbon will get deposited on the spent catalyst. It will further come into the region. Here burning will happen. Though the reaction vapor mixture, we uh, will come through the reactor vapor line to the main fractionator column. There in fractionator column, different valuable products separation will happen. So now the here I was telling two part I'll discuss. One preheat section. This is the RR section. Now into the region, if you see, we have two double stage cyclones are there. Here basically cyclone purpose I told you. Objective is to here whatever the catalyst we are getting here spent catalyst after burning, because air is then directly it will go, then catalyst loss will be there, huge loss of catalyst will be there. So we need to separate the air from the catalyst after burning. So in cyclone that separation will happen. Then the after the flue gas after burning, it will go to the through the we have an orifice chamber. Their pressure drop will happen. After that, it will go to waste heat recovery boiler. We got a power plant basically. In power plant, it will go. There will recover the heat. After recovering heat, that further that flue gas will go to the FGDU, flue gas desulfurization unit, for the treatment of this flue gas, so that acidic content H2S and all we can remove. And after treating the treated flue gas, basically CO2 will be exposed to the atmosphere, right? So this is how catalyst circulation will establish. Okay, is that clear? So as a summary I'll tell the reactor major components of RR. If you see it here, feed nodules will be there. Through that feed will come. Then BSS termination device, what you're telling here, BSS termination device will be there. The cyclone separators. In reactor, two single stage cyclones are there. In region, two double stage cyclones are there. Then MAB, air will come through blower, a grid will be there. It's not like directly it will go. Air grid will allow how the air pattern will flow, and will make sure that spent catalyst fluidization should happen into the regenerator. That kind of air grid will be designed condition. The reactor stripper basically stripping off. This is the reactor stripper, basically stripping off the hydrocarbons from the catalyst. The reactor region auxiliaries will be there. Auxiliaries basically what are the instruments and all, slide valve and all, hydraulic all system, that I'll not be will be discussing because it is taking a lot of time. Only 10 to 15 minutes only pending. So I'll try to cover in that time only main fractionator column and then gas concentration unit, right? This is the diagrams and all. It will take more time. Just overview video I'm giving, so I'll not explain into the design part. So as I was telling that, right, we'll discuss into the four parts. So you can see it here, two part already over feed preheat section, RR section open. Now fractionator section I'll discuss. Okay, 1 minute. I'll change it. Is it shared now? So if you see it here, I was telling, right? Wait. You can see it here. I was telling feed preheat section, which I explained already. Then RR section I explained. Now I'll discuss fractionator section, then gas concentration unit. These two sections I'll try to complete within 5 to 10 minutes, right? Just wait. 1 minute here. I'll take water, then you ask. Okay, please ask. Basically, grace catalyst we are taking. In that catalyst composition part is there. Okay, if you ask now, I'll tell only. Wait, directly you ask now. Okay, okay, just this is the FCC catalyst. You can see I had that already. This is the FCC catalyst. In that four parts are there. You can see it here. One is zeolite is their major component. Total FCC catalyst comprises of four parts: zeolite, matrix, binder, fillers, and additive. So zeolite is basically primary active ingredient, and this is the acidic site chemistry, and this basically control activity and selectivity. And the material, you can say, ultra stabilization rare earth on ion exchange will be there for the geolite composition. This is the major is geolite. So catalyst we get basically grace catalyst we get. Now matrix will be there, basically active matrix including outer geolite surface area cracks heavy molecules and other functional matrices. Then binder will be there, what will be going to basically make sure all the other components are grouped together for that glue. Binder basically glue, it is glued 20 to 30%. Some of the catalyst it will be there. Then fillers will be there, kaolin clay. In that, whatever the gas will be there, the kaolin clay will be filled 20 to 40%. And the additives basically, these are the main four major component of catalyst. Additives is basically to change the reaction pattern. That if you want to increase, we want CO generation, COP will be adding. So like COP or jettison will be there, SOX and oxidator. So CO promoter objective is to whatever the regeneration, CO generation is more. So COP will add so that CO immediately get burned into the COT. This is the catalyst we use, and these are the composition of the catalyst, right? Clear? Okay, any doubt? Okay, so I'll try to complete, okay? Main fractionator section bit. Okay, so what happened, that reaction vapor I was telling now, around 520 degrees Celsius, that will come into the bottom of the reactor. Here quenching will happen because fractionator, how the fractionator column will operate, it's a basically multi-component distillation. Basically different components we will be separating based on its boiling point, right? So basically vapor mixture will get it here. Here some label will maintain directly. It will here in that the slurry is there, right? From its PA pump around will be there. Will be giving it here for the quenching purpose. So it will cool. Further circulating oil will get after heat recovery. Further it will come here PA around pump around for the uh, giving cooling to the reaction vapor mixture. Further HCO heavy cycle oil we get for its pump around will be there. Similarly LCO light cycle oil we are getting, its pump around will be there. Then here top product will get LPD, light pressure distillate. Part of that LPD, light pressure distillate, will go as a column as a reflux. So basically the delta T in get like whatever the withdrawal temperature we are maintaining is basically uh, this PA flows will change. If the temperature we want to vary uh, of the draw, then this PA flows will vary accordingly, will maintain the column profile. Again, column profile maintaining itself a big subject. That will some you can read it or can ask some other people if you join an industry, because explaining everything here in 10-15 minutes is difficult only. It's itself a very big thing. In the internal components and everything will be there. So as of now, what you can understood here, basically in fractionator column, whatever the reaction mixture we are getting from the reactor, we'll try to separate it. These are the products we get it. Here we'll get LPD, light pressure distillate, and the gas will get both will go to the GCU unit, gas concentration unit. Their separation of the product will be happen. There will get ATG, LPG, and character naphtha. So this part is again on another section. In main fractionator column, LCO, HCO, CRO, all these get, and CLO will get. So I was telling now, key feed and this is the product. So product separation will happen into the main fractionator column. Our main fractionator column consists of 41 trays. Bottom 1 to 6 like this and donut type is there. 8 to 12 trays are packing time is there. Then chimney trays are there. Basically withdrawal, whatever the withdrawal we are getting is basically chimney tray. Chimney tray is like a explaining. Okay, wait. If I have chimney trays, you can see it here. Here chimney trays wherever there, here withdrawal will be there. DO means draw temperature drop will be there. Here we'll get a withdrawal that will go to the pump section. From pump will keep running. So for a pump to run, minimum level required, right? So that pump should not cavitate. So in the chimney tray, this is the chimney kind of shape will be there. Here label will fall. It will getting filled up till here. Then after that, here holes will be there. Through holes it will fall to the. It will try to reaction by permixing and will try to fall to the bottom, right? The vapor will go through that. After that, the liquid will also come through that. It will fall to the bottom. So this hold up will be there for the draw purpose. Suppose where are the locations where chimney tray will be there? So you can see it here. Whatever the draw off is there, draw off means whatever the draw off we are getting. Suppose LCO draw off. So here chimney tray will be there. HCO draw off, here chimney tray will be there. CRO draw off, here chimney tray will be there. So wherever draw off is there, their chimney tray will be there for maintaining a minimum level so that pump should not cavitate. So that different type of trays is there. The rest all trays are wall type trays. Okay, this is all about main fractionator section. This is the trays and all I cannot explain in details. Now further comes the GCU section I was telling. So GCU you can see it here. Whatever the products here is there. So here we'll get a in main fractionator column reaction vapor mixture and it will go through the main column over condenser. It will build up some label and the gas will try to go to the compressor will be there, wet gas compressor, and the liquid part will go to the LPD, light pressure distillate. It go to the HP receiver. The total section separation section we call it gas concentration unit. That I'm going to tell now. From gas concentration unit, we'll getting three products. One is LPG, ATG, and then CRN. So you can see it here. This is the main column over receiver. Through the gas will go to the wet gas compression. Here pressure of the main over suction pressure of WGC will be around 1.85 like that or 1.8. From main column overhead receiver, then it goes to the pump WGC to suction. In between KOD will be there. Suction KOD, this gas will go to KOD. After KOD, it will go to the wet gas compression. Because why KOD is given, basically whatever the liquids entrainment liquid is there, it should not go to the compressor because compressor is a rotating equipment. If it hits even a single drop of the liquid hits the compressor impeller, it will damage immediately. So for the same purpose, the KOD it will go to suction KOD. Then after that, it go to the compressor. Compressor it will compress it. After compressor, it will go to the HP receiver. After compression, this is showing a gas concentration unit. It will to the HP receiver and the liquid LPD, light pressure distillate, will have a through the pump. We call it a LPD pump. Through that, it will again come to the HP receiver only. So from HP receiver, we'll have a two stream. One liquid holdup will be there, other high pressure gas will be there. So it will be around 14 kg will be there in that. So top of the gas from the HP receiver will go to the primary absorber. Primary absorber basically whatever the suppose lighter naphtha content is or the carryover is getting happen through the CRN. Again, we'll put the naphtha, we'll try to absorb it. After the primary absorber, it will go to the sponge absorber. Basically, here we'll get in primary absorber, basically any LPG content or naphtha content is there, we'll recover it. Further, if any naphtha carryover is there, we'll try to recover in the sponge absorber. We'll get a sponge absorber media as a HCO, lean HCO. The top product will be fuel gas. It will go to the SRE unit. SRU for further treatment. Okay. Now the bottom product of HP receiver. This is called HP receiver. HP receiver. From bottom HP receiver, it go to the stripper. We have a GCU stripper will be there. In the stripper, basically will strip off any gases are there or lighters are there. C1, C2s will strip off. When heating media will give a boiling temperature will take. Then bottom of HP receiver will be a feed to DB1, DB2. We have a 2 dB column in FCC2, DB2, D-bit nozzle column and DB1. So what is the objective of D-bit nozzle column? Can anyone explain? LPD goes to HP receiver. From HP receiver to GCU stripper will come. From stripper it will go to DB column. Anyone heard of D-bit nozzle column during the college time? Okay, see. As of now, whatever the products we extracted from them, already LCO we extracted, ATG I told, HCO, okay, you receive already, then CLO also. Only two products pending, right? What are the two products? See, this one you got, CRO you got, HCO you got, and fuel gas also got. Only two products are pending that we get from the GCU section. What? LPG right now, LPG and CRN, right? The objective of debutonizer column to separate the LPG content from the naphtha content. So it will go to the DB column. Here reballing will maintain from tray 3 and then reballing will give a, then top will maintain a minimum tray temperature so that at that particular temperature this separation can happen. So the objective of DB column is to separate the LPG from the naphtha, CRN, cracked and naphtha. So here bottom will get a cracked and naphtha, CRN. This bottom also will get a CRN. This feed will go here also and then further it will go as a feed to DB1 also. Bottom CRN will get. Top product what we get, it will through the condenser, it will go to the overhead receiver. From overhead receiver as a pump, it go to the reflux. Then other pump will be there, other pump will be there. This is got LPG. From LPG, similarly here also overhead receiver will be there, reflux pump and LPG pump is there. Both will pump out and it will go to the Marox unit. The LPG will go to the, this LPG will go to the Marox unit for further treatment. After treatment, it will go to the bullets. From bullets, it will be sold to the bottling units for in bottles, whatever the cylinders we are getting, the cylinders will be bottled up and it will be sent for the selling purpose to respective gas agencies. Now bottom CRN will go to the MS block. MS block, reactor and naphtha basically. Their treatment will happen, whatever the sulfur impurities and all there, that removal will happen in FCC and HT. After removing that CRN will get, that is basically treated CRN is basically petrol, reactor and naphtha that will send to the blending pool. From there, it will be blended with whatever the petrol we are getting from MS block or directly naphtha can get blended if it is treated. And this is the one of the products CRN, reactor and naphtha. So all will be blended together and to maintain the particular composition at what particular spec petrol is going to sold, so that we maintain and it will be sent into the blending. From there it will be sent for the selling purpose. So this is all regarding FCC block. So almost our overview part is over now. Okay, meantime just this is something I'll tell you must know. After that we'll close the session. Okay, different types of crude and its effect on FCC. See, crude, correct? Where we get the crude we get from where? Anyone regarding crude? Can anyone tell? What are the source of crude we get? Normally, we have a crude in India like Mumbai High, Assam. It is there. Okay, or else mostly be imported from the Middle East countries or USA or Russian crude be imported. So the crude type and its composition will vary. Some crude will be very high in that sulfur content will be very high. So there are three types of crude classification will be happen. This is the heavy, this is the medium, and this is the light crude. This is heavy crude. This is the medium type crude will be there. This lighter. So heavy crude is there means in that carbon generation, coke generation will be more. It wants bus very heavy. Regenerator temperature will shoot up. If the medium type it is there, it will be balanced, moreover balance will be there, no problem. If rava is there, lighter crude is there, if you process, in that carbon will be not there. For maintaining the reactor region temperature, we need carbon, right? So if carbon is not there, it will not burn. So region temperature will start dropping. So in order to make up, we separate, we give as a torch oil, we give into the regenerator for burning. Basically, torch oil basically cutter kind of diesel we burn indirectly there. So for FCC to run smoothly, we prefer either kind of like medium crude is there, then it is very good for a person who is sitting on the DCS or control room. It is very good for them to operate. Lighters is there, then if it becomes certain emergency can create after one region, after one in heavy, very heavy there region behind burning can happen. There are emergencies in happen. FCC can happen. So basically in FCC, it's not about the as a DCS officer or a shift in charge. Our objective here is to ensure whatever the products we are making here, it should be on spec. Second, any emergency comes into the plant, we should be able to handle either any pump trips, moon blower trips, separately, because electrical equipment, anything can trip. Lot of upsets will happen. We play here with the temperature and pressure. See how much temperature is there. 530, 700 degrees Celsius temperature is there. Anything problem comes, suddenly the temperature profile, RR profile will vary like anything. It is very difficult to handle. So as a plant operation, we try to understand not overview in depth of the plant. So when you guys try to come industry, this kind of training will be given. If you if you guys come into the industry, because you are virtual, if you are in the refinery, we should able to show you plants also, equipment, reactor, region, everything. We can show the physically, because in the plant seeing animation and the real plant is very difficult, very different only, totally different. So you cannot have a total grip, but overview part, I guess you can understood it here. So guys, any questions? If you guys want to connect, like our LinkedIn already, ID is there. Alok Moria will be there. You can search it is there. You can connect with me for further doubt and all. You can on LinkedIn you can send and reach out to me. Okay, then we'll close the session, right? Okay then. Thank you. Thank you guys.